Hello, my name is Rendy. I'm Senior Data Manager from Ruang Guru, education technology company in Indonesia, and we'll talk about how to use deep learning on big data and what are the lessons learned. Let's get started. Right, so the title of this talk is Deep Transfer Learning on Spark Dataproc using Keras on UDF. So first, we'll talk about the use and the data that we'll use. But first, we would like to also talk about our session objective. First is we would like to learn how to actually do deep learning on big data, because when I try to do so, there are not a lot of reference out there. So it's a bit question here and there on how actually do deep learning on big data, and in this case using Apache Spark, how to actually achieve horizontally scalability in at ease, right? So that's one objective they would like to achieve, and the second one is how actually cloud can simplify things, how using big data technology, which is quite complex, can be a lot simpler using cloud, right? So those are our session objectives. And about the use case, what we are trying to do is we would like to classify X-ray images, whether it's COVID or not. So given X-ray images, we'd classify whether a capture of X-ray for a patient has COVID or not. And we will use anonymized X-ray photos. And this is one example that is taken from the data set. And this is the source of the data that I'm using. So we are using a COVID-19 radiography database, which is built by a team of researchers from Qatar University and also Bangladesh, and with collaborators from Pakistan and Malaysia. So there are medical doctors and collaborating on how to create merge databases of chest X-ray images for COVID-19, along with other disease as well. Related to lungs, right? So you can take a look at the paper to see the data set closer. And this is the structure of the data. So there are like around 3,600 files of COVID with other X-ray images for lung opacity, normal lungs, and also viral pneumonia. And we have the specification of images in 299.299 pixels with density 72 pixel per inch. And all images are grayscale because this is X-ray capture, right? So they are all grayscale. And this is the model. So after we talk about the use case that we would like to classify whether this is X-ray images for COVID or not, we would like to talk about how the model will be implemented, and starting from the architecture itself. But first, I think just to be on the same page, in case some of you haven't heard about deep learning is a subset of machine learning. So this is one of the methods in machine learning, which basically, if you ever heard about neural network, it is neural network with 3 or more layers, right? So it tries to aim to simulate how actually brain cells works. So if you have brain cells with dendrite, which is connecting from one to another, and there are some electrical pulse that is going here and there, right? So it tried to simulate that by having some kind of like neurons. If you see the circles on the picture with all the edges there, and there will be weights in the edges that will be training from the training data. And when we are talking about deep learning, it actually perform a lot better when you have a huge amount of data. So deep learning comes a lot better if you have like thousands and thousands of data. And actually, since it requires training from a lot of data, it means also bigger computation needs as well. So you need bigger computer or more computers in order to train deep learning. And it empower a lot of use cases, interesting use cases, for example, like self-driving cars, language translation, or probably generating scripts, or even art like paintings, right? So those are interesting use cases that can be done by deep learning. And the next one is transfer learning, because the talk is more about deep learning using transfer learning, right? So think of transfer learning. Basically, you are training on something and you use the knowledge to do something else. So in this image, you can see there is a deep learning network that is trained on classifying panda. So it can do classification on giant panda, red panda, raccoon, or the class of panda. And then we use the same model without any changes to actually produce features which can be used to classify something else, like for example, dogs or chihuahua, right? So basically, it tries to train data on something and then use the weights that is written in each of the ages in the neuron of deep learning for some other use cases, right? So this is the transfer learning that we are going to implement as well. And this is the architecture of the overall model that we like to create. So basically, X-ray images from the chest would be our input, and it will be fed into the ResNet 50 deep learning architecture, and it will produce features. Then the features itself can be used to train any classifier model that would like. Like for example, in this case, I'm using logistic regression, but you can also use other classification model. This is just for example, right? So we have a logistic regression trained on the features that is produced by the ResNet 50 from deep transfer learning. So basically, what I'm trying to do here is trying to replicate what is done in this paper. If you can see on the left bottom, it's written by Ben Brahim, Hachimi, and Amin. So it's basically trying to implement the deep transfer learning on Apache Spark. And next, we'll talk more about the technology, right? How actually to implement the Apache Spark on Dataproc for the deep learning. But first, we need to understand what the technology that we are using. So if you haven't used Spark, basically Spark is one of big data technology out there. Big data technology means a technology that can process a huge amount of data in scalable manner, and Spark is quite widely used. It's used by a lot of people, and it gains a lot of tractions as well in the community. It's horizontally scalable, means you can add more machines, like small machines, in order to get more compute power, and it can process data in parallel. And the most important thing of big data, it needs to be fault tolerant, since you will deal with probably like tens or hundreds of servers. It needs to be fault tolerant. If one of the servers goes down, then you need to be able to carry on the process. And I think the one that makes Spark widely used is it provides data frame API. So if you're a data scientist, you used to work on your local laptop, and then you would like to use big data, you can use Apache Spark quite easily because it provides data frame. Usually, data scientists use Pandas data frames, and on Spark, data frame is there as well. And for those who are more comfortable with SQL, like SQL language, basically on MySQL, PostgreSQL, or whatever databases that you have used, SQL can work as well on Spark. So the support of the API is quite broad. That makes Spark more widely used. And what we are going to use on the Spark itself is IPython notebook. So we'll use the notebook to run on the Spark as an engine. And to make it simpler, we run the Spark on Cloud Dataproc. So basically, Cloud Dataproc is a managed Spark cluster provided by Google Cloud. You can, so basically, on my experience using big data, it's quite hard for you to combine all the open source out there. And you can end up focus more on infrastructure and less about the use case. And we would like to do the other way around, right? We would like to focus more on the use case, right, and less about the infrastructure. And this Google Cloud Dataproc make it easy for you to configure. You can just specify what you would like to install on the cluster, like IPython notebook or Apache Zeppelin or other open sources big data out there. You can specify what you would like to auto scale up, down, what's the minimum server, what's the maximum of the auto scale, and what's the most important is also for auto kill to save costs, right? So here it's very important because big data will use a lot of servers in a cluster, and if you don't auto kill when you don't use it, and then we will end up paying something that you don't use, right? So this auto kill feature is also very important, and it's there in the Cloud Dataproc. And this is the overall system that we would like to implement for this use case. So basically, I will store the extra images on something called cloud storage. This is basically a virtually unlimited storage for files on Google Cloud. So I have like probably 30,000 of extra images or to 20,000 extra images, and I can upload it in cloud storage without any limitation and then read it using Spark on Cloud Dataproc and write all my codes on IPython notebook. So basically, this is the overall architecture that I would like to implement in this use case. Right? So that's the system. Probably some of you like show me the code, right? How's the code being written? So this is it. So basically, first we'll read the files, of course, from the Google Cloud Storage. Basically, if you see here gs colon and then slash slash, right? This is the address or the bucket that you would like to have in the Google Cloud Storage, and we read it using spark.read format. Basically, you do a recursive read and then you load it into a data frame. So this is how the Spark read the images from Google Cloud as a binary file. And then after you read the images, remember that we are doing transfer learning. So we download the model and we see the weights from the model that is pre-trained. So it's trained before, right? So what we are using is StressNet 50. This is the deep learning model. We download the model and we also download all the weights with it. And remember that Spark is big data with a lot of servers in the cluster, right? So we need to broadcast all the weights to all the servers. So all the servers has the knowledge of what are the weights. So basically, if you see the code here, sc.broadcast, basically it sends all the weights of the model into all the servers, so the servers have it. And in this model underscore fan function, we basically try to call the ResNet 50 constructor. We create the model and we set all the weights based on the data that is broadcasted before. So this is the transfer learning that's happening here. And if you see here on the model.summary code, I try to take a look at the architecture to see whether I download the right ResNet 50, right? Because you need to verify the architecture of the model itself as well. Okay, so that's the transfer learning. And then after I do the transfer learning, then I call the image, the model in the function called featureize series. So in this function called featureize series, basically I call model.predict, which means I call the deep learning model and I predict the data from the input, and it then returns predictions of the data, which is actually not the result whether it's COVID or not, but it's a feature. So it's called featureize. So the deep learning model will then output the features. And if you can see here in the pre-process function, I actually try to kind of like adapt the function, the image that we have as an input, because we need to adapt the input so that it can be used by the ResNet 50. And one of the process being done here is trying to resize the pixels, because for before it's 299, then I resize it to 224. And I also, since ResNet 50 only accept RGB image, red, green, blue image, then and the input is only grayscale, I try to copy all the images or channels into all the red, green, blue. It's kind of like having 3 layers of grayscale. It doesn't affect the result because the image is actually the same. And then after we declare the preprocess and featureize function, basically we call the function on the Spark ML pipeline. So here is actually the classification part. After we get the feature from the deep learning model, and then we use a label indexer to say, okay, this is lung opacity, this is normal, this is COVID, this is pneumonia, right? So I use a label indexer here, and then this label indexer will go into the logistic regression model, where we train using some kind of like default parameter here and see whether it works or not. So basically, we define the pipeline here using array. If you see here, stages equals to array of label indexer and then logistic regression. So you can put more pre-process if you want to. This is how you define ML pipeline on Spark. And after you define the pipeline, you then start to train. And this is similar to sklearn or other machine learning library out there. You call fit and then you train against training data, which I do split here. and it start to train the data. It takes about 2.5 hours, I think, using like 16 core of cluster, right? That's the logistic regression pipeline, and this is the prediction. We try to run the prediction on the test data. It's we call Spark underscore model and then transform, and use the F test split as the parameter there, and then we show some of the prediction. And as you can see in the table here, we have 5 prediction, and I think 4 of 5 get it correct, like 332200, but one of them get it incorrect, right? Prediction is 0, but it's actually 3. And as I told before, that we use label indexer. So index label here probably 1 equals to pneumonia, 2 equals to COVID. I don't know about the number here, because it can be dynamic all the time. But this index label here is actually whether it's COVID or not, right? Right? That's the prediction part, and this is the result of evaluation here. So I think I haven't told you that my basics is more about data engineering and less about data science. And this is the first run that I've tried, right? So the result is not that good. It's 89%. So it depends on the business, but for healthcare, 89% accuracy is very, very low, because you need to aim for 99 and more, right? Because some of disease is actually quite rare, that you need to take a look at some of the zeros behind the commas even. So this is the result of evaluation. This is also done on Spark. We can see I put some of the metrics here, and also the area under curve, the error seek diagram, and also some confusion metrics here, right? So, what can we learn from the whole process of the training, and then predicting, evaluating on big data? Is actually, first, deep learning actually can be simple. So some of you might be discouraged with the complexity of deep learning itself, but since we have transfer learning here, you can start and try on transfer learning first and see whether it works or not, and start to build your own architecture if it somehow doesn't work, because we have a lot of the trend is going there, right? Using the pre-trained model, try it out, quick and dirty, and see whether it works or not. So if you would like to try something out, then you might want to try the transfer learning out, right? That's the first learning. And the second is actually, when I use my personal laptop, it takes like, I don't know, 10 hours if I remember correctly, like 9 to 10 hours. But with Spark, I can just tell to spawn more nodes, and it can be done a lot quicker. So I can do a lot of iterations in one day, compared to just waiting in my local notebook. And I think that another lesson learned is using cloud can make it a lot simpler, personally for me, because I used to combine a lot of open source, and sometimes when I, for example, use Spark and then HDFS and some other big data open source, the versions doesn't compile from one to another, which is quite tricky for me to find the right versions and then make it work. And I end up wasting time there. Instead of doing that, you can just use what is provided and as a service. For example, in the screenshot here, I just click the web interface, I click Jupyter, and then it will runs the Jupyter on top of the Spark, and I can start to do data science works with on steroid, because it's run on top of a big cluster. Like, another learning is the tech is okay, but the important thing is also, of course, the end results accuracy, right? So this is something that might be a future work to kind of like try to improve the accuracy, because the one that is written in the paper itself, it achieved like 98 to 99 accuracy, which is quite far away from what I've done in the first run. Probably I need to do a hyperparameter tuning or something like that. But I think the point of this talk is how we kind of like implement the technology all together in order to do the deep learning on big data, right? So yeah, I think that's all from me. We can go to Q&A. Thank you for listening. Feel free to post your questions. Right. I think while waiting for the question, um, this very method can be used for other purposes as well. Like for example, recently, just this morning, I tried the very same method to predict several time series data using FB Prophet. So if you ever use FB Prophet model to predict, you can do the training and predictions using UDF for some cases. Like in my case, I use 4,000 cities, and I parallelly train data on those cities to predict the temperature of the day. So it's basically used for predicting global warming. But in order to make it faster, I implemented on Spark on UDF as well. So calling the same method can be used for other purpose. Right? Yeah, for TensorFlow self model, that's this very good question. I haven't tried it before, but essentially for UDF, as long as you have the TensorFlow self model weights broadcasted to all the Spark machines, you basically can call any Python functions individually on the Spark workload. So basically, UDF is you are calling a vanilla Python functions, right? As long as that TensorFlow self model can be called using a vanilla Python, then it will be possible to do so. But I haven't tried it before. Thank you for the question, Jose. Right. It's been great. Thank you very much for the questions, and I hope this small sharing can be helpful for you guys. Thank you. Bye.